All right, so just hope that the exchange between Cliff and me will go okay. I'm stepping in today, and I'll be back again next Friday. Before we move forward, just had one quick question. Though we tried very hard to avoid, not having to ask you to come at hours other than the class hours. So next Monday, meaning this coming Monday, turns out we have to cancel the class because of unavoidable situation, meaning Cliff has to be somewhere else and that sort of thing. So just for this particular class, would Friday, evening, late afternoon work for the whole class, for if we want to have an extra class next week? Late afternoon, or we can do like a 5 p.m. thing, we'll get pizza in the end or something like that. Will that work or not? Yes? Okay, that's enthusiastic, yes. Okay, good. So good. So I'll also poll again. Just don't want anybody to miss it in case we have it. So, yep.
So it's next Friday?
Next Friday, yeah.
Next Friday, like at around 5 p.m.
Yeah, it depends. We are a little flexible. I can do 5:30, start a little later if there's, just so that people can attend. One extra class. And so, yeah. I'll send out an email. By the way, all of you are on that Google list, email list. You receive the emails now for the class, right? So, yeah. Okay. Good. So, and the other thing is the second assignment will be posted today. It was supposed to be posted yesterday, but it will be posted today. Okay. So, I think you have moved. I saw that Cliff has really taken you to a very nice point now. Just in terms of the book, where are we now? We are done with 1 and 2 chapters, 1 and 2. 2 is ray tracing, ABCD matrices, introduction to ABCD matrices. And hopefully you are comfortable with it. You had a couple of problems in the first assignment just to test it. But in the second assignment, you'll have a lot more thing to play with, more realistic laser design situations. Okay? So, in fact, you have gone quite a bit beyond the ray tracing and ABCD matrices now. One of the important things with the ray tracing chapter was the test for stability, which I think you know that there is a stability criteria. After you, I'm just going to do a very quick, overview of what you have done till now. So with ray tracing, once you determine your ABCD parameters with lenses, with mirrors, and things like that, then if you end up at the same point as you started in the same material medium, then I think we know now that AD minus BC will be equal to 1. Only if you end up in the same material medium that you started from, right? If you go from air to water, you are not, and you're looking at a incident in air and transmitted in water, then this will not hold. There will be some ratio of refractive indices and that sort of things. The stability criteria was A plus D plus 2 by 4 is less than 1 and less than 0, something like that. Right? So I think you have derived that, right? Just what does that mean? It means that if I have, let's say, even intuitively, 2 classical mirrors, and if I start bouncing rays between the 2, will it stay within, or will it kind of escape, right? If it escapes, then it's not stable, right? So, and it can escape if if this criteria is not met, right? So that's a very quick summary of and then the mechanics of ray tracing is very intuitive. There are some if you know how to deal with lenses, with mirrors, with different curvatures and that sort of thing, right? So that part is yep.
So when the light leaves the mirrors, how do you make sure that it's all parallel? Because it's going from a variety of angles when it's
when the light leaves the mirrors, how do you ensure that it's... So in the ray tracing, as you know, it's one ray, right? Is that what you're asking? It's parallel to, meaning...
the light that leaves the mirror, how do you make sure it's
right. So, you can look at a case which is, very clearly unstable, right? So, if you start out a beam that is parallel here, that will clearly escape, right? I mean, so, right? Now, are you asking how do you ensure that if I have multiple beams escaping the cavity, they all remain parallel?
Yeah.
Right. So, if they don't, then typically you try to do something outside here to bring it back. Because it's a laser, you still have coherence and you can really refocus things, right? And we'll see unstable cavities are useful for very high power lasers later. And that we can, I don't know whether I actually understood your question clearly. Yeah, sorry.
I think you're asking if how the rays comes out all collimated from the laser. Like if in a stable system, how does everything come out like straight collimated?
Is that what you want to know? That if you have a stable system, why does it come out collimated, or why? Okay, so that part, meaning why does it remain coherent? Right, so we are going to actually start talking about various aspects of it today with resonant cavities and why is it that you can maintain coherence for the light that comes out. We're going to start talking about it. But the general fact is we are doing everything to ensure that the light that, if I have a stable cavity on the other hand, and I have light bounce back and forth, forms a Gaussian beam, spreads a little bit, right? It has its beam waist here and then kind of spreads and matches on two sides. And then part of it is going to leak out. We will let it leak out, otherwise there's no use of the laser, right? We want the light out, right? Now this part we'll actually, the coherence of that is really whatever light is coming out is of the same phase with a certain spatial delay phase factor, but if it's coherent here, it continues to be coherent here. So whatever comes out continues to be coherent, and that we are going to actually discuss in great detail. But if your input of the light here is coherent, then it will remain coherent here, and it may not remain parallel. Typically, it will never remain parallel, as you know. It spreads out by your angle, theta, which goes as wavelength over the diameter roughly, right? It spreads out. It's not quite parallel, but the phase fronts are coherent, and that means if I put a lens, I try to focus it again with design it by ABCD matrices, and you can kind of make it come back and have a certain amount of Rayleigh range. It will remain. I think you kind of have started looking at this sort of a design, right? Every time you want to focus, then it defocuses a little bit, right? But parallel, remember the ray tracing is just the center of that beam. It says nothing at all about how the beam is shaped. Is it Gaussian, Hermite, or whatever? It doesn't say anything like that, right? Ray tracing is just the center or the optical axis of the beam. I don't know whether I'm going in the right direction towards the answer, but the part of the coherent, why is it coherent? Why does it remain coherent? Is because we are really selecting out one mode. Once we put the cavity in, it selects out one mode out of many possible modes, and then that mode has only one frequency and one wavelength. And when it comes out, its phase front will follow whatever is allowed by the electromagnetic, Maxwell equations. It will follow that, and you can redesign it and make it parallel. When we say parallel, we just have to be clear what do we mean by it, because it's a beam. It has an electric field profile that's kind of a little more spread out in this direction here. Here it's a little more peaked, the electric field profile, and then it kind of spreads out again a little bit, right? So, okay, perhaps if it's not clear, we'll kind of continue discussing this aspect. Yeah. Okay, so one of the major things you did really after the ray tracing that Cliff did was develop this idea that not all waves, and especially not laser beams, are an infinite parallel plane wave, because that's not terribly interesting for the laser. We want to spot, and by taking various beams and making some of them go at slight angles and all that, and adding them all up, you can create a Gaussian beam where instead of a magnitude of or intensity of the electromagnetic wave being completely on a plane here, it is really concentrated, and then it dies off exponentially as you go away from the center of the beam, right? So that's the Gaussian beam, and this is a quick review. And one of the things that I wanted to talk about today was the Gaussian shape is only one of many possible modes of a laser beam. There are a few others which have nodes and multiple spots and that sort of thing, and they have their own uses. But how did you get to Gaussian beam? Again, I mean, we said that let's assume that the electromagnetic wave here, the laser beam, be it here, wherever it is, here, it's propagating in a uniform material medium, and then we assume that the electric field, instead of being a plane wave, right? A plane wave looks like e to the power minus j k z with E naught as a vector. A plane wave would look, where the electric field is just oscillating in say the x direction, y and z, and the wave is propagating in the z direction, so electric field kind of oscillates in real space, and magnetic field goes that way. And the plane wave says that if I am at this point in x, y, or I'm at that point in that plane of x and y, wherever I am, my maximum field is exactly that. Right? It's the same amplitude, so the whole wave front. Whereas the Gaussian beam, we allow for the fact that no, I don't need my electromagnetic wave to have the same amplitude over the entire plane, xy plane, but it may be a beam which is concentrated somewhere near the origin, right? And in fact, what we find is we allow for that, and the way Cliff did it was you say that I'm going to allow a certain amount of radial and z longitudinal distribution of this electric field, and the vectors are very clear, hopefully, which way the fields are pointing and all that. So this sort of a behavior where this is obviously 1 for a plane wave, but now we kind of allow for a little bit of a change. And then when you take this and essentially say that is such a electric field profile allowed, and the answer to that is if it satisfies Maxwell's equations, it's allowed, right? So whatever satisfies Maxwell's equations for wave propagation, so n can be the refractive index, so this is basically k squared for you, right? Times E is equal to 0. If it satisfies this equation, it's allowed, right? So you plug it in here and then kind of crank through it, and what comes out after that is what is your psi r comma z. In fact, you get another equation on psi, this lateral spread of the wave of the electron, or sorry, the electric field, and it basically, I think, looks something like 2k times psi over dz is equal to 0, something like that, right? So you said what we get is, yes, this sort of thing is allowed as long as psi follows this sort of equation, right? And then now you have to solve this differential equation. This is transverse, which has only x and y components of the double derivatives of the Laplacians, and then you try something, and what you tried was the Gaussian form of the psi. So what you tried there was psi will kind of start out with a maximum value at z is equal to at xy is equal to 0, and then as I radially go out into sort of a cylindrical geometry out here, as I radially go out, my amplitude will decrease, right, as a Gaussian, and that essentially looks something like minus r squared. And I think I'm not going to go through the math again, but you got a lot of useful stuff out of it, like what is the effective beam, waist size, and the diameter, and what do they depend on, and all that, right? So the way you tried it, if you remember, is we said that let's try psi of r comma z to look as some p of z plus k r squared by 2 qz, or something like that, right? Something of that sort, and then said you try it, then you figure out that you have two equations for p and q, and you had this nice little very important relation of q, which is get a z plus jz naught, and related now to all these very useful laser parameters. Z naught was what, 2 pi square of the beam diameter divided by the wavelength, and then all kinds of other things like that, right? So, and then here's the, whatever you get here is where your beam has the narrowest waist, right, or the beam width, right, and so on, right? But the end result of all this is we got a full-blown, nice expression for the electric field, and it has all these factors for a Gaussian, right? That's what we got, a Gaussian, and the Gaussian looked like this. It had, so we can kind of divide it by the maximum amplitude of the field, but then the shape of the field, how does it look in X, Y, and Z, looked something like, there would be Z, e to the power minus, and then it died off as a Gaussian, right? So something like that. There's a radial factor with a distance and all that. And then you had a propagation factor, e to the power minus j, kz minus, again, I'm just going to write this down, and I think you have already seen this, but I think it's good to just have a short review of that, because that will lead to why do we have higher order modes. So you got this propagation or a longitudinal phase factor. I think hopefully the name is very clear why it's called longitudinal, because as the wave propagates along the z direction, that's the longitude, that's how the phase is changing. This angle theta is changing with z. Right? So if you didn't have a Gaussian beam, if you had just a plane wave, this will be there won't be this, right? This tan inverse. Remember, this thing came from your E of z. That's where it came from. Right? So yeah. If you did not have this, obviously you have just e to the power minus k, and that's just the plane wave, which is uniform everywhere. There's no psi. You can see that's that. And then you had this radial phase factor, which looked like it was curved. That's what leads to this curved phase front. This curved thing that it actually starts curving like that. Leads to that curved phase front, and this is the radial phase factor, right? So that's how things are changing with this, and then I think you have all these expressions for the radius of the phase front. When it curves, what's the radius of that sphere that contains that little curved patch and all that. So that was. Anyway, if you remember, it has expressions, well, like R of z is equal to where you are in z, 1 plus z naught over z whole squared, right? Something like that. So that's your radius curvature and all that. Right? Anyway, hopefully, I'm just recounting what you have done earlier, right? And I think Cliff has done some very beautiful examples with this as well. But I want to just say that this is not the only solution. As you know very well, that yes, you found a solution, but now you must account for the fact that there's a possibility that there are other solutions that look kind of like this, but may not be exactly like this, and all of them are still allowed. Right? And I think you know that the moment you get something that looks like a Gaussian, if you have done, if anybody has done other courses on EMAG or quantum mechanics, you would realize that that's the wave function for a harmonic oscillator. The ground state wave function is a Gaussian, and then the moment you go to the first excited state and second excited state, you develop nodes, right, and so on. And exactly in the same way, the electric fields allowed that satisfy Maxwell's equation for a laser, for any electromagnetic field for that matter. The psi is not, this is not the only choice. There are more. And that's why I just want to kind of point that out, and then when we need it, we will kind of go back and look at it. Okay. So anyway, so this is essentially what we just wrote down, the whole Gaussian beam, and this is called now a Hermite-Gaussian beam, which is a more generalized form of it. Okay. And what is the change, right? So the change is really two things in this whole expression. There are only two things that change, and let me basically just write those things down first. So first of all, this Gaussian we'll write it not as r square anymore, but write it as e to the power minus x squared plus y squared by your beam width, beam diameter squared, minus the whole thing. Okay. And the reason I'm doing splitting out x and y is because now some modes will preferentially have nodes along x, some of them will have nodes along y. So it will split into, the x and y may not be exactly the same anymore. And as a result, that part is also, so E, we write it as x, y, and z. The electric field. In fact, let's forget about the vectorial nature. We understand what that is. And in front here, we will now have to say that which mode is this. I mean, the Gaussian happened to be the 0, 0 mode of a much bigger set of possibilities. And those modes now are, when we go and try to solve an equation like that, we get these Hermite polynomials, and I'll write it as hm and hn, right? So there's no space here. So hn, and let me just write this, hm and hn. And these Hermite polynomials are with some arguments which, let me write that down. It's square root of 2 times x over the beam width, or the diameter, square root of 2 y over the diameter along z. So that's how it looks. So this thing is actually here. So these are two factors which are no dimensions and all, but just numerical factors that appear. In fact, I think in the book it uses m and p because n has been used for refractive index earlier. So that's one change. The other change, it really, this expression is the same, but now we have split out here x and y. And there's one more change, and that's in front of this phase factor, the tan inverse part, not in the propagating part, but in the tan inverse part. So let me also expand that out, the longitudinal factor. And the reason I'm saying this, trying to get into this little bit of a complication is because it is useful for lasers. And so let me write that down, 1 plus m plus p, where m and p are the orders of the mode, and tan inverse z over z naught. Same thing as earlier. So what happens is you have this little extra factor of 1 plus m plus p, where m and p determine the mode of this Hermite polynomial or the oscillator. So lateral modes. And these are integers, zeros, ones, twos, and all that. So for the 0, 0 mode, m is 0 and n is 0. M is 0 and p is 0. That's the Gaussian mode that you already have done. For 0, 0 mode, h0, h0 of this are 1. 1, 1. And you get Gaussian, you get a 1 here, you have already done that. But now we go to a higher mode, m is equal to 1, let's say. M is equal to 1, and let's say p is equal to 0. Right? Now this thing will not be equal to 1 anymore, and this will still remain 1 because p is 0, it still remains 1. But this will not be equal to 1. The way it will look, now the Hermite polynomials are, essentially if you want to find the mth order Hermite polynomial, it's, minus 1 to the power m, just a sign factor, even and odd, plus and minus signs, e to the power u squared, the mth derivative of e to the power minus u squared. So you take e to the power minus u squared, take, if you want h1, which is what we need there, you just take first one derivative of e to the minus u squared, and I think you'll get u times e to the power minus u squared, right? And then e to the minus u squared, e to the u squared cancel, and you just get something which is proportional to u, which is linear function. So what I'm trying to say then is h1 of any function x or u is proportional to u. There may be a 2 or something, I'm not bothering about that right now. You can always absorb that into your coefficient out here. Similarly, h2 of u will look like 2u squared minus 1. And I think we know already h0 of u is equal to 1. So, yeah. And I think you hopefully see now what it does. Immediately you see that along the x direction, if I'm looking at m is equal to 1 mode, then I have to choose 1, and there will be x here, there will be because of this x. And instead of this coefficient looking like, if I were to plot now along the x-axis, y-axis, and z-axis, right? And I look at the electromagnetic mode. I'm not bothered about all these other details, these radially dying and all that. The phase factor also I'm not terribly worried about. Remember, this is a much slower changing thing. This is faster and all that. So I'm mainly interested about these Hermite functions that appear in the front. I think you see right away that if h of u is equal to 1, you have a function that looks like that. At all x's, it's equal to 1. If I have u, it's a odd function, right? Positive for upper half and negative for a negative. U is equal to, for n is equal to 2, it looks like a curved number, right? I'm just plotting. I don't know, it's kind of not a good way to plot it, but I'm just plotting the value of the Hermite polynomial as a function of x, right? So constant, linear, u. So what it does is takes whatever electric field that was radially symmetric, which was Gaussian, right? A radially symmetric electric field that was a Gaussian, and this function gets multiplied with that, right? So as long as you are constant, you get a Gaussian beam. But the moment you get to the first mode, m is equal to 1, you get a 0. This thing gets pulled down to 0 now, right? And you get a field that would look like that and like that, right? Electric field, right? Negative and so the electric field now would be oscillating. If you're if you are in a positive x space here, let's say the electric field is oscillating, in this direction. If you're out here at the same point of time, it would be oscillating out of phase now. Does it make sense? Electric field is opposite in sign if you move to the other side. Right? And there's a node, there's a point along the beam axis. It's 0. There is no electric field left anymore, right? So, I think the power of the laser is proportional to square of the electric field. Power of any electromagnetic field is proportional to square of the fields, and therefore the square of the field looks more like, like that, right? So you have two beams really now going. Right? And then when you look at it from a far field, you'll see two spots now on a mirror, right? See a spot that kind of has a W naught of that. See a spot like here, and then it will have a little, fading out. There's another spot here. I think by now that, this is exactly pi 180 degree out of phase with that. It's the opposite direction electric field, right? You take it to another mode, the next mode, I think you can see you'll get, something like that. You see 3 spots. These are all with just m, which is the x mode. You get splitting in x now, right? Now you can turn on your y too, and then you can see you can have all kinds of, you can have also splitting in this direction now, right? So you have this spectral modes, m and p, therefore determine, how many spots and that sort of thing, right? So how many nodes really is that's the count of how many nodes you have. M is the number of zeros if you move along x, and p is the number of zeros if you move along y. When you look at a spot and you see 4 nodes, it's, along x-axis, you're in that mode. That sort of thing. Yeah. And you realize right away also that these nearest neighbor ones are typically out of phase by pi because of this. So you have these physically, physically separated beams like that. Is that clear? Yeah.
I don't get
Sure.
where the Hermite polynomial came from. Why can't you just multiply it with the Gaussian?
Where it came from?
Yeah.
Yeah. Okay.
Why can't you just do that?
I try to skip that justification, but essentially what you have then is once you plug in this equation, Gaussian is one solution that works, but it's not the only solution. Right? Any polynomial which has this form, any function x, y, z that has a form of Hermite polynomials p, y. When I write x and y, I hope you see, you just have to kind of substitute these little factors out there. No function takes a dimensional unit as an argument, as you know, so you have to divide it by all that stuff. I'm just kind of, but then, 2rz. Basically you have these, this is, let's say, and then a minus jkz. So if you take this and substitute it here, it works for every Hermite polynomial. In fact, this is guaranteed by a mathematical, the nature of this equation is actually very similar to the simple harmonic oscillator equation in quantum mechanics, which has exactly the same solutions. Everywhere that this equation appears, it has the same solution. It's always Hermite polynomials. And the 0,0 mode of that is the Gaussian that we talked about earlier. And the moment you go to higher modes, you get all these other nodes. That's it. Just to be, analogy to quantum mech, your ground state wave function looks like that. First excited state would do that. These are all also Hermite polynomials in quantum mechanics. Same deal. So yeah.
When you say higher modes, does that refer to the frequency inside, like the frequency inside cavity or something?
Say that again.
So when you say higher mode, does that refer to the higher allowed frequencies inside the cavity?
Oh, okay. Thank you for asking this question. So, actually, not quite. This is additional. This is just related to, by clever design of the cavity or the lenses and all that in between, we can select out a few modes. And the cavity, what we want to see now, is the cavity. One of the main jobs of the cavity is to select out a mode. You have all these modes always allowed. These modes are always allowed, but the way you design your D, if you put a little thing in between and all that, you select out a few modes and allow only some to oscillate, and the other will die out. They won't be able to self-sustain. They will all die out. So essentially, what you will end up doing is you will pump all the energy of different modes into one mode. So you make it that's the typically, if you want a single mode laser, that's what you do. Sometimes you want multi-mode lasers too. Yeah.
When you say mode, the mode refers to the one frequency wave.
Right. So if I have also if I have a cavity, let's say just a simple two mirrors, and I have a distance d, and I think you already, if you remember, we talked about you have all these different allowed frequencies. Now any number of half wavelengths are allowed, right? Now what we are trying to say now is, within this picture itself, if I have, we already have these modes already allowed. These are modes allowed by the cavity. But Maxwell's equations allows you more. It's saying that, well, wait. This is just a plane wave that you have asked me to solve for. What if I don't have a plane wave? What if I have a Gaussian? What if I have Gaussian of the MP order? Then I have all these other possibilities, and therefore you have these other extra modes now. These are all extra, in addition to what is allowed for a simple plane wave. Yeah.
Are all these modes assumed to be orthogonal to each other?
They are actually orthogonal, as in if you take the product of the two, if you take E10 and take E20 star, and you integrate it over any period in space or in time, you will always get a 0. And anything to do with energy and observables, you're right. They're orthogonal. Intrinsically, these are orthogonal. HM and HP will be orthogonal, and yeah, very similar to if you have done the quantum, the wave functions will be orthogonal. Yeah. Okay, so why are we even talking about this? First things, there are very simple things why this may become useful. This is some made up, not really made up. People actually had to deal with these issues. If you have mirrors and you have this Brewster angle gain medium, and let's say there's some defect right in the middle of your Brewster angle, and the Gaussian beam has this maximum intensity at the defect, that's a bad idea because it will absorb a lot. And so sometimes you want the beams not to go through the middle of the that's kind of a little made up. You can clean this up and all that. But sometimes what you also want is so if you had a hole coupled mirror, meaning you had a hole in the middle to get the light out in the end, the laser from a tabletop laser, and the diameter of that will determine how much light comes out from this beam. And the way to select out, for example, let's say you have a beam that has, let me draw it here. So let's say you have a beam that looks like this, and somehow your laser has started oscillating such that you also have another mode, which is this one. Right? We have two modes now, let's say, and they're propagating. And then what you can do is I think you can see that there'll be some amount of beam spreading, but I think from your earlier classes with Cliff, you know that the beam spreading is really minimal. There is always beam spreading, but over a finite distance of a meter or so, you go from maybe 1 millimeter to 1.01 millimeter on the other side. It really looks, it's pretty collimated. Only if you go to the moon or something, it will start spreading enough. So you can put in essentially, a reflector or something of that sort here, which, all right. So I think I kind of didn't draw it right, but it will look something like that. So essentially, you can cut off these two beams by just doing that. It's a physical filter which filters out the central beam, 0-0 mode, and rejects the other mode physically. Obviously, you will also lose a little bit of that, but then there's a lot of other engineering that goes into kind of fixing those issues. Does that make sense? I mean, this is a physical filtering. If you've done electrical engineering courses, you do all this in frequency domain. This is in real space domain. You just kind of say, well, I know my beam width here. That's like W naught, or something like that at Z. My W will flare out a little bit. W at Z is equal to I think you have these formulas now, 1 plus Z over Z naught whole squared, right? It spreads out, and then you determine what should be the size of this, put that here, and it cut out, remove some of the modes. Similarly, you can have other fancier modes. If you have other modes with, like that, you can cut them all out. And if it's a good mirror, you can feed it back into the cavity and recover that energy, so you don't lose that energy either. The other reason why the modes are important, here's how it will look. If you take the squares, it will look like a spot for the 0-0 mode, 1-0 mode, 2-0 mode, and all that. The other important reason is the following. Okay? So, and this is related to you talked about these ABCD parameters, right? And you talked about the cavity. So one of the most beautiful results of the laser physics, at least, is that if you have any sort of a Gaussian beam, whatever you had talked about, the self, the fact that Q at point 2 is equal to A Q at point 1 plus B over C plus D, right? This is a very nice result. So it tells you how your beam parameter Q propagates, right? Where is your Q? I mean, it's buried inside some of these parameters there. That Q over there. So as it propagates, you can use your ABCD matrices to completely say how the Gaussian is propagating, because once you know Q, you know everything about the Gaussian beam, right? And all of them pretty much hold exactly the same for Hermite higher order beams. It doesn't change at all. It's the same. Second thing is, if you talked about, very importantly, the stability criteria, meaning if I have a cavity that looks maybe like this, and then a mirror like that, in anything you choose really, and then you'll have a beam that kind of will flare out a little bit, here. You have go out, and then the curvature will increase a little bit, so that it exactly matches on both sides. The only modes that survive here are the ones that match on two sides, right? You talked about that, right? So essentially you look at what would be the R at 0 here. So let's say this is D. The R at 0 would be infinite, right? This flat mirror. And R at D would be whatever is the radius of curvature of that. So those are your R parameters. And then from there you can kind of figure out what is Z, you figure out W naught, all that stuff. Right? The beam width that's allowed to be able to manage to do that and all that. And then you had, if you remember, the very important result there was all the modes that are allowed in this cavity. Now this is a cavity, right? And all the modes, those are allowed. You don't have to have a cavity. You generate a beam, let it go. This is an allowed electromagnetic wave. Right? Now, once you put it inside the cavity, which you need to do for a laser, not all modes are allowed now. Only certain ones, right? As we were trying to sketch, only certain modes are allowed. Right. Which modes are allowed? The ones that will allow all this matching on two sides and all that stuff. Right? Those are allowed. And you also saw the kind of which modes are allowed are obviously given now by considering a round trip round trip around this cavity, it must come back to itself after you do a round trip, right? This is very important. One of the most, I think, amazing results of laser physics, which, according to your book, there's no explanation why, why ABCD works, according to your book at least. So, but it works, and I think you guys got donors just for that, right? Somebody should figure it out. But it's a beautiful result that if you say that it comes, if you kind of start out here, come around, come back here, get your ABCD matrices for that trip, then it must satisfy this. If it doesn't satisfy this, it's not an allowed mode in that cavity. That's what it means. So the only modes that are allowed in that cavity will be the ones that satisfy this. Then ABCD parameters are very easy to get. I think you have enough. You'll get a few more problems to practice, but it's very easy, and so it's a nice result. And you get from here that 1 over q as a result at any point z. I think you have this what is that, pi, and I'm just writing this down because once you get these parameters, you also get all your radius of curvature, or rather the phase front, r, and the w naught and the beam widths, all of that you get it from here, right? So, right. So one of the very important things. Wait, what are we doing on time? We are over time already? Oh no, we have some time left, right? 10 minutes, right? Yeah. One of the very important things is that so these modes are allowed, and your beautiful ABCD result tells you which modes are allowed. One of the questions we want to ask is, what is the volume of that mode physically, the spatial volume of that mode in centimeter cube? What's the volume? And the reason for that is, as you know, just putting a cavity like this is not of much use till you have gain in the medium, right? We want to have optical gain in the medium to make it not die out. You need, you have a resonator plus a gain will give you a sustained oscillator, and the gain is always by stimulated emission. That's what we use in a laser, stimulated emission. For that we need matter. We need to put in some atoms, or a quantum well, or quantum dots, whatever gives me my stimulated emission. So I will need to populate this region with my gain medium, right? And the question is, if I populate this medium with gain medium and the gain medium is outside of my mode, it's useless. Right? It's not doing anything. It's not seeing that electric field at all. Right? So the gain matter should be inside that volume, and the question is, what is that volume? Right? So that's the mode volume. The gain matter should be placed inside the modal volume so that you are able to get your stimulated emission. One photon comes in, two out, and all that stuff within that mode, right? So the question we are asking now is, what is the mode volume? And I think a first guess, a very simple guess at the mode volume is the following. So you know that your beam width is roughly w naught at the thinnest point, right? Roughly w naught. The distance here is d, right? Let's assume it's a cylinder for all argument's sake. Let's assume it's a cylinder. We know it's a Gaussian. It dies down and all that. And just to account for that Gaussian, let's say that the radius instead of being w naught is like w naught by a square root of 2. I think that's what it comes out to be. That's order of magnitude. So in that case, if I have a cylinder of this is my radius and that my distance is d, then I think you can say right away that my modal volume should be very close to pi d over w naught over root 2 whole square times the distance or the height of that cylinder, roughly. And you get half pi w naught square times d, right? So that's a modal volume with this very crude approximation. Now this only will hold for a 0-0 mode. I think the moment you go to M and P, you are in a bit of a trouble. You have to be careful because there are many beams now, right? There are like 2 beams or 4 beams or 8 beams, depends, right? So you kind of sum them all, right? So you have to calculate a modal beam volume depending on all modes properly now, right? Now how do you actually do this? And we'll see that the actual answer is this times the factorial of the mode number m, factorial of m, factorial of p, and times 2 times m plus p. That's what we're going to see is the modal volume for the MP mode. I hope you see I'm mixing up approximations and exact. This is exact for any Hermite-Gaussian beam. Gaussian beam is a part of Hermite polynomials, so we call it a Hermite-Gaussian beam. This is the exact result for the modal volume. 1/2 pi W naught squared D m factorial p factorial to the power m plus p. And you can put m and p is equal to 0, 0. You get at least an intuitive answer, zeros. So that 0 factorial is 1, 1, and 2 to the power 0 is 1. You get something that seems reasonable, right? I mean, volume is diameter, cross-section area times the height, thickness or the length. So, and I'm going to just, in the interest of time, just outline how you do this. I think you know that the atoms in the cavity will interact not with the electric field, but the electric field squared. So the way we write this out is electric field squared is equal to E star, right? And what did we do in our analysis here is we wrote down a big expression for the electric field. Here's electric field. Take this, take its complex conjugate, all your exponentials, complex things just go out of the window, they're 1. Right? Go away. And you're left with only the real parts, this one and the Hermite polynomials. Take absolute squared, integrate, and you have beautiful results of orthogonality and all that with Hermite polynomials. Once you do that, let's say E squared, right? Once you do that, you can say that my volume of MP mode times the electric field squared maxima is equal to, essentially what I'm trying to say is you have now spread over x and y. It's not uniform. The electric field is not uniform, but over x and y it's spreading, over z it's spreading a little bit, right, changing. You have to integrate it now over x, y, and z, right? You have to do a dz, dx, and dy, and then you have to have your e, x, y, z with all your Hermite, polynomials, Gaussian, all that stuff. Just plug it in here. Do this whole thing. Y, what are we going to integrate over? Y is the lateral dimension, right? The entire plane, right? Entire axis, minus infinity to plus infinity, minus infinity to plus infinity. What about z? Z is the longitudinal axis inside a laser. The 0 to d, the cavity length, right? So 0 to d, right? So you do that, and what pops out from there is exactly what we wrote here. Oh, sorry, I think this is what you get once you do that. That's the mode volume. And the thing is, the mode volume is, interestingly, you look at it and you say that, well, if I have a Gaussian beam with MP is equal to 0 and 0, 0, 0 mode, then this is my mode volume. I have W naught squared, D. D is, the laser cavity length, right? I mean, that's physical. And W naught is the beam parameter. Yeah.
In that last expression, shouldn't be some dependence on the amplitude of the electric field?
Oh, very good point. So you see the amplitude, it's a very good point. Actually, no. It doesn't have a dependence on the amplitude of the electric field. The amplitude of the electric field says how much energy can I dump into that mode. That's a measure. But no matter how much energy I dump into it, if I increase the energy of a mode, and let's say the mode was something like that, in the xy direction, the electric field profile is something like that. If I increase the amplitude of the electric field, so at every point the electric field amplitude is just going to go up, but really the intensity decay, as you go away from the axis, you have this W of z, which is the W parameter. It has no electric field in it. So it still stays, the diameter doesn't change if you just increase the intensity. It's just at every point the intensity has gone up more. If you look at it classically, the electric field amplitude has gone up at all points, but it doesn't change. You yank this up, but it kind of doesn't change the full width half max and all that. It doesn't change. And quantum mechanically, it changes the number of photons in each mode. The number of photons in each mode just increases it. It doesn't change the shape and all that of the beam. It's an important result. Yeah. Now, what I wanted to kind of end by saying today is this importance of this volume is striking if you just do some numbers here. Let's say you have 0.1. What was the example we had, or rather, I think there was a similar example discussed earlier. But let's say your D is about 1 meter, and W naught is the beam diameter, about a millimeter maybe, roughly 1 millimeter. And then you can kind of see it will be close to, if you take the volume, just that without all these factorials, and this is for the ground mode, about 15, or what was it? I forget. I mean, about 10 centimeter cube or something like that. That's how the volume would come out. Or you can just run the numbers. You know. And now you say I'm going to make a helium neon laser, which is one of the most popular lasers, you know, with the lambda naught of about 632.8 nanometers in the red to the eye. That's the wavelength. And I think wavelength, you know, it goes into this W naught parameter, right? It depends on the wavelength. And that means I have helium neon gas atoms inside that mode volume. I have atoms of helium or neon. I mean, neon is kind of the primary stimulated emission element, you know, neon. And it's sitting there. The neon atoms are sitting there. And you know your volume, right? And you now have to know how much gain do I want. So that determines what is the pressure of neon in that chamber. How many atoms are there depends on the pressure. Higher is the pressure, more are the atoms in there. Right? So the number of atoms is dependent on pressure. Let's say I think there's an example in your book of 0.1 torr, you know, lower 1,000th of atmospheric pressure. Atmospheric pressure is 760 torr, right? So this is 1,000th of atmospheric pressure. At atmospheric pressure, you have roughly 10 to the power, roughly 10 to the power 20 atoms per centimeter cube. This is, I'm just kind of doing it very crude way. In atmosphere, if I had just atmospheric pressure of neon, I would have about 10 to the power 20 atoms per centimeter cube. That's the number roughly called for a gas. And, you know, an electron gas would have 10 to the power 20 per centimeter cube electrons. And a gas of atoms would have this many for atoms. Now with 0.1 torr, you will have, about 4 orders lower. So 0.1 torr would have about 10 to the power 16 neon atoms per centimeter cube, right? Roughly, order of magnitude. Yeah. Then I take that and I multiply that with my mode volume. That will tell me how many neon atoms are there in that. This is very important. How many atoms are there in that mode, in that volume? Everything else is useless for me, right? Only those will give me gain. So it'll tell me, well, you have this many, and then for a laser, what we will be doing is we'll be exciting this with some sort of a broadband light source, and it will absorb the light and then do stimulated emission. And let's say from here you get about 10 per second absorption of a photon. These numbers we'll see in detail later, but each neon atom, let's say, is absorbing 10 photons from the broadband light source per second, and it creates stimulated emission. Right? And when you combine all these things, and the photon energy is about, from this wavelength, this is about 2 electron volts. You can multiply all these things together to get about, you will get about, like 5 milliwatts of, you will get a power output. So 5 milliwatt of energy will come out. 5 milliwatt of output power at this red wavelength will come out from this laser, if your mode volume is that much. And you see, now you are kind of stuck because you say, well, I want more power. This is too little. This is a standard, if you worked on a helium neon tabletop laser, this is a standard number. I mean, this is not too far off. Right? You say, I want to increase my power. You see, D, physically already we're at 1 meter. You can obviously make it larger, but there are issues with making things much big. W naught is dependent on the wavelength and things. It's also very restrictive. It doesn't give you much. Obviously, you can see, I can go to higher modes now. I can have, 3 and 5. I suddenly get a very large improvement. And yes, you will, but it will be multimode, right? So there are these restrictions, and one of the most important thing is you can increase. You can keep your mode volume fixed, but you can really increase the number of atoms, and that's what a solid does. A solid material has a lot of atoms, right? So a solid will have, it can have 10 to the power 22 per centimeter cube, close to, that's the atomic density of solids. So that's a gain of going to dense material media. But then there are other issues as well. If you have more atoms, you will have absorption and all that stuff. So we'll see that later. But hopefully you see multimode feature can enable, some things, maybe higher powers, and also how do you kind of do why should the volume of the mode be important? That's the reason here. Okay, good. So we can stop the class today, and next Monday, Cliff will get you started on this chapter. By the way, so we are done till chapter 5 in your book, and we'll start up on chapter 6 now. Yeah.
Thank you.